Hey, hello. Let's get started on the second part of the homogeneous catalysis. So, shown on this slide, that's what I showed you guys last lecture. So those are elemental reactions. Okay, we call them as. Let's use a different pen here. So this will call that as elemental, mentally. Oh, elemental reactions. Okay. So they are basically reaction reaction modes or reactivities of transition metal complex. And last time we showed you we can combine these reactivities for reaction with a homogeneous catalyst. We can use this reaction these reaction modes to develop reaction mechanism, catalytic mechanism for reaction by a catalyst. Okay. So last time we showed you the well-known Wilkinson catalyst. That's a rhodium chloride triphenylphosphine. Okay, that's this catalyst. Okay. So hope you guys can record how that works, and for this class, okay, so you can understand the example I showed in this class. Then pretty much you can master these elemental reactions. Okay, then also you can use this example to review how to electron counting, how to track the oxidation state change, and also the coordination number change, and geometry change of a catalyst during the catalytic cycle. Okay, so that's we talk about discuss the Wilkinson catalyst for the hydrogenation of alkene molecules. Okay, so moving on, in this lecture we'll talk about several different examples. Okay. Yeah, let's change my color. Yeah, in this example we are going to talk about we call that methanol carbonylation. So that's a very famous reaction. So that's actually it's industrial process called Monsanto process. So probably you guys have heard about Monsanto company, and because of the GMO product. I know lots of people don't like the GMO product. So this process, you can convert methanol. Let's start with methanol here. That's your reactant. So you can convert, that to acetic acid. Use rhodium or iridium catalyst. So in this slide, where I'm going to discuss the catalytic cycle, use a rhodium catalyst for this conversion. We call that methanol carbonylation. Okay. So the initial state is here. That's we call that state A. That's a dicarbonyl. Okay, dicarbonyl. So the basic question is so we can let's do it from here. Okay, so we have rhodium here, right? So rhodium, so we have 2 minus ligand, 2 neutral carbonyl ligand. They are 0 charge. Then what's the oxidation state for rhodium? So overall it's a minus charge. So we have what? That's going to be +1. That's your rhodium. Okay, rhodium. Then what is the electron counting for A? How do you do electron counting for for the rhodium A compound. Okay, so rhodium, how many electrons we have? Rhodium 1. Okay. Yeah, rhodium 1. So rhodium 0, how many electron for rhodium 0? Okay, think about that. Okay, then rhodium 0 is D9, right? So since it is a rhodium plus here, then we have 8 electron, right? Then we have 2 iodine ligand, then 2 times 2. Then we have 2 CO ligand, 2 times 2e. So what's the total electron count here? That's 16 electron compound for rhodium A. Okay, rhodium A compound. Okay, that's a so that's a for coordination. Okay, coordination number is 4. Okay, so then let's look at the first step. Okay, first step. So we have methanol. Okay, it undergoes hydrolysis to produce methyl iodide. Okay, methyl iodide. So that's a separate chemical reaction starting from methanol to produce methyl iodide. Okay. Then what we have is yeah, it's it's not meth. It's kind of but I'm sorry, it's not meth, and that's not hydrolysis. That's actually is a acid base reaction. Acid. Okay. After the formation of methyl iodide, then the rhodium A compound rhodium A here, okay, can react with methyl iodide to form this rhodium B intermediate. So what's this reaction? That's a oxidative addition. Okay, so right now your rhodium become rhodium 3 plus here. Then your coordination number is 6. Right now it's octahedral compounds, right? You have 6 ligand. Then, so what's the electron counting? 4B. Okay, make sure you can practice by yourself. Okay. Then we can say we have the oxidation of rhodium increased by 2, also coordination number increased by 2, right? Then what's the next step? So next step is you can say, so we have methyl minus ligand here, right? Then we have 3 iodine anion ligand here. So then we're going to have, we call that migratory insertion reaction as the next step. So what happened is the CO bond, one of the CO ligand here, it will insert into rhodium methyl bond. Okay, then you are going to end up with this methyl acyl group. Okay, so that's acyl. That's acyl group. Acyl group. Then what happened is, what's the oxidation state here? Okay. Okay, what's the oxidation state for rhodium here? It's still rhodium 3. Okay, rhodium 3. Okay. Because here that's still minus acyl is minus ligand. Okay, and then ligand. So still rhodium 3. Then right now coordination become 5. Okay. Then how do you do electron counting? Okay. What's the electron counting? Okay. All right. Then next step is what we have is ligand addition. Okay. Ligand addition. So one external cell will take the open side from compound C. You're going to have compound D here. Okay. So that's a neutral ligand. So we still have no change for the oxidation state. Okay. Then what's the next step? So next step is going to be the reductive elimination. So the AC group and iodine ligand will form bond from carbon iodide bond. Then you get rid of this, you know, uh, you know, sort of acyl iodide product. Okay, acyl iodide product. Then your catalyst, you can see it goes back to the rhodium one in the initial rhodium A state. Okay, then they form this rhodium, the acyl iodide can react the water from here. Okay, from here. Then that's called hydrolysis. This step. This step is hydrolysis. Then you make the acetic acid, and you resume this iodide, this hydrogen iodide. Okay, so so that's a whole catalytic cycle. Okay, you can say we still involve oxidative addition, ligand, micro insertion, and ligand addition. So last of it is reduct elimination. Okay, so that's a Cn equals 6. Okay. Then you can say we have, the whole can cycle here. So, but the one thing I want to point out is the function of hydrogen iodide here. So, in principle, okay, after a catalytic cycle, we do not consume hydrogen iodide same as this rhodium A catalyst. So this one, that's a cold catalyst. Okay, it also a part of catalytic cycle, but it's a cold catalyst. This hydrogen iodide does not, it does involve reaction, but does not change after the reaction is finished. Okay, that's a cold catalyst. Okay, that's this methanol carbonylation. That's very famous reaction. Okay, Mansando process. So this process is actually one of the most famous large scale industrial application of homogeneous catalyst. Okay, and that has been used ton scale. It's a very large scale reaction. I think right now, this reaction still has been still used by several companies like Dow Chemical. Okay, Dow Chemicals. Okay, let's talk about a different example. Okay, I think we mentioned that palladium catalyzed CC bond formation reaction before, right? In this reaction, in this slide, I'm going to give you a specific example to strengthen the understanding of the concept of homogeneous catalysis and also the different reaction modes of transition metal complex. Okay. So palladium catalyzed reaction for CC bond formation have been very useful to make organic molecules, including pharmaceutical molecules, organic materials, and agrochemicals. Very useful. So here I'm going to show you one example of palladium catalyzed CC bond formation. Okay, and we are going to you can learn more other palladium catalyzed reactions, coarse carbonyl reaction, CC bond formation, coarse carbonyl reaction in the future. Okay, I'm going to use one example to show you. So let's see. We started with state A. That's the initial state of the catalyst. Okay, so in this cycle, we started with palladium 0. So palladium. That's this reaction is CN coordination number equal to 3, and we can still do electron counting. Palladium 0. How many electron? Palladium 0. Okay. That's 10 electron. Okay. We have 3 ligand, 3 phosphate ligand, 3 times 2. So that's a 16 electron compound. Okay. The palladium compound E, that's a 16 electron species. Then this compound, that's a 3-coordination compound, so it can undergo oxidative addition with arrow bromide. Then you form this Cn equals to 5, okay? Coordinate number 5, palladium species of B here. Then, so that's 2 plus, okay? Your oxidation is changed for palladium. So that's oxidative addition. The next step is, that's 5-coordinate species. It still has, can react with another substrate. So what happened is we have what? That's a, ligand exchange reaction, okay? So ligand exchange. Okay. So here, right? So you have ligand exchange. Then the another substrate, that's alkene substrate, replace the one of the phosphine ligand. So you still have this, 5-coordinate species. That's compound C here. Okay, palladium C here. Then what happened is, so after that, what happens? What happened? Another step. Okay, so what happened is, you have this, anion carbon ligand. Then, it will undergo, 1-2 micro insertion. Okay, so this, sorry. Let's go back. Okay, sorry. Go back. So here, okay, so that's 1-2 micro insertion. So the CC double bond will insert into the palladium phenol bond, carbon bond, okay? Then you are going to make this, a new, let's change the color. You are going to make this new carbonyl ligand, okay? Carbon anion ligand. Right now, you see your coordination become a coordination equals 4 species, okay? So what's oxidation state here? Oxidation state, okay? Think about that, okay? Then what happened is, okay? Okay. Then that's a simplified magnet. So you are going to have the beta hydride elimination, okay? So one of the the beta hydride, okay? So it's going to be here, this hydride will undergo the beta hydride elimination. So actually, let's put in this intermediate here, okay? So we are going to have this intermediate. So let's add an intermediate here, okay? Let's add as a D prime here, okay? What's a D prime? So let's draw it, okay? We can draw it here. So that's the after beta hydride intermediate, you have this palladium hydride intermediate. That's become 5 coordination species, okay? Then the hydrogen bromide can undergo so that's reduct elimination here, okay? Then you form this 3 coordination species. That's your alkene product here. That's an uniform alkene product here, okay? So then 3 coordination species. So that can undergo the ligand exchange reaction. So the phosphine ligand replace this alkene ligand. So that's your product. Okay. So here is your reactant. You form reactant. So then your cat goes back to the initial trace phenyl triphenylphosphine palladium 0. Okay. So that's one of your reactant. So here is reactant 2. Okay. So the overall reaction is, this aryl bromide plus an alkene with palladium catalyst. You form this new alkene product. So what happened is actually that's you form a new carbon bond here. Let's use a different color to emphasize. So here is new carbon CC bond formation, okay, and you get rid of this as byproduct, okay. All right, let's change my color. All right. So here is another example. That's alkene polymerization. Okay, alkene polymerization. So I just wanted to briefly mention this reaction. Okay, because polymer materials have wide applications in our daily lives. Simply speaking, polymer materials are the base for any plastic stuff we are using in our life. Okay, like plastic cup, plastic bag. They are all polymers. Okay, then I'm gonna show you how transition metal complex can be applied as catalyst for producing polymers. Okay, so I'm gonna briefly mention that how that works. So normally you can start with a metal hydride. Okay, metal hydride. So what happened is this metal hydride, okay, can react with the alkene monomer, okay, alkene monomer. So you have alkene is migration insertion into metal hydride bond, okay. Still 1,2 micro insertion. So you get this alkene product, and then you can repeat this alkene 1,2 micro insertion. Okay, you can increase the length of this carbon bond here. Okay, here is 1. Right now, increase the length to 2. Okay, then you can repeat the reaction. Okay, just repeat the reaction. You can increase the length of this, ethylene polymer. Okay, or you can the polymer. Okay, then you undergo beta hydride elimination. So what happened is this one of the beta hydride here, the carbon, the attached carbon. Okay, here is alpha position, here is the beta position. And go to beta hydride elimination, you can go back to the metal hydride, then you release a polymer. Okay, polymer. So the polymer, when the number n greater than 100, we call that polymer. Okay, that's in this case the polyethylene. Okay, that's polyethylene. Okay, that's reread. Polyethylene. Okay, here if n equals 3 to 100, we call that onigomer. So then here it's dimer. Dimer, when reaction stop at n equals 2, that happens. Okay, when the beta hydride takes place after n equals 2. Okay. So that's why. So the beta hydride image can takes at any point n equals to any place. When you add here 2, you get dimer. When you get n equals this time, you get onigomer. and when you get here, you get polymers. Okay, so that's another example to show you how we use microinsertion and the beta hydride elimination to for a metal hydride catalyst to produce polymer or dimer or oligomers. So mainly we want to emphasize the polymer formation. So that's a chain. Here is chain growth mechanism for the formation of polymer. Okay, I think I'm going to stop here for the example of homogeneous catalysis, and hope you guys can pay attention to the reaction mechanism for this several examples. And I believe if you understand these reactions, you get the essential launch point for homogeneous catalysis and also the reaction modes for transition metal complex, or organometallic complex. Okay, pretty much. Okay.